Here's a second example of a related rates problem. This problem says that gas is escaping a spherical balloon at the rate of 4 cubic centimeters per minute. How fast is the surface area shrinking when the radius is 24 centimeters? So we recall that the formula for the volume of a sphere is 4/3 pi r cubed, and the formula for the surface area of the sphere is 4 pi r squared, where r is the radius of the sphere. So first let's take the equation 4/3 v equals 4/3 pi r cubed, and we're going to take the derivative of both sides of this equation. So we get dv dt, since we're assuming that v is a function of time and that r is also a function of time, we're going to take the derivative of v, but then on the right side of the equation, when we take the derivative, we'll be taking the derivative of the r cubed function. So we have 4/3 pi multiplied by the derivative of r cubed, which is 3r squared times dr dt. And then simplifying this, we see the 3's cancel, so we get 4 pi r squared times dr dt. And that's equal to dv dt. Now if we go back to the original problem for just a moment, it tells us that, it asks us, first of all, it tells us that gas is escaping from a spherical balloon at a rate of 4 cubic centimeters per minute. Now that's dv dt, the rate at which the volume of the gas is escaping from the balloon. That's dv dt. So on the right side of the equation now, we know that this is 4. Or on the left side of the equation, rather. On the right side of the equation, we have 4 pi times r squared, but then the problem tells us that it asks us how fast is the surface area shrinking when the radius is 24 centimeters. So we're going to replace r by 24, and we'll be squaring that, and then multiply by dr dt. Now, we're going to want to solve this equation for dr dt. First of all, we notice that if we divide both sides of the equation by 4, we get 1 equals pi times 24 squared times dr dt. Right? And then we can rewrite this as dr dt is equal to 1 over pi times 24 squared. Okay, so that's a good result so far, and we're going to use that on our next slide, because the question asked how fast is the surface area shrinking when the radius is 24 centimeters. So we're going to want to use the surface area equation, which is s equals 4 pi r squared. Let me clean that up a bit. I can do a better job on pi. Okay, now we're going to take the derivative on both sides of the equation. So we have ds dt, which is the rate at which the surface area is changing, is equal to 4 pi multiplied by the derivative of r squared, which is, so that's times 2 times r times dr dt. And so multiplying this out, we get ds dt is equal to 8 pi times r times dr dt. But we know two things. We know that r is 24, and then we also know that dr dt is 1 over pi times 24 squared. So let's plug those in. So 8 times pi times 24 times dr dt, which was 1 over pi times 24 squared. Okay, so use a little red ink here. We can see that the pi's are going to cancel, and we see that one of the 24s is going to cancel. So consequently, we end up with ds dt is equal to 8 over 24, and that reduces to ds dt is equal to 1 over 3. Now our unit was cubic centimeters per minute, was the rate at which the volume was decreasing. So that means that this is going to be centimeters squared per minute because it's an area. So the surface area shrinks. At 1/3 of a square centimeter per minute. I suppose I should write these out as minutes. Okay, and that's our answer. So there is another typical related rates problem.